All right, here's another question. It's actually we got a lot of work to do with this question, but it starts out with, it's actually a two-parter. Which acid has the stronger conjugate base? And then it's a pH question after that. And so the first thing we have to remember is that if we think about a hypothetical acid, then when we use this equilibrium that shows this hypothetical acid breaking apart, we have an equilibrium constant. And what we need to remember is that the stronger the acid, the weaker its conjugate base, and vice versa, right? The stronger the base, the weaker its conjugate acid. And so what we have to do is we have to compare the two Ka values. And remember, the larger the Ka, the better that particular substance is at forming products. And in this case, the better it is at being an acid, donating a proton. So what do we get? We get that the larger Ka is the stronger acid, thus the weaker base, and the smaller Ka is the weaker acid, thus the stronger base. And so the smaller the Ka value, the stronger the base. And so we look and we see large Ka here, strong acid. We see small Ka here, weaker acid. And so we know that acid 2 must be the stronger base. And so now what we have to do is we have to completely think of something different now. Now that we've thought about that equilibrium, the next part of the question is saying, what's the pH of the solution of 0.234 molar of that particular base? And so we have to write down the equilibrium expression of a base acting on water. Now, when it comes to the hypothetical weak acid equation, you can neglect the water because HA can break up into A minus and H plus, and H plus and H3O plus are the same thing. When it comes to the equation of a base, you can't neglect water because there's no way to get OH otherwise. And so what we need to do is we need to make sure to have water included in the equation as far as writing down the equilibrium. But of course, it's not going to be included in the equilibrium expression because water is going to be a liquid. And so this particular equilibrium has an equilibrium constant, and that equilibrium constant is the Kb, the equilibrium constant associated with the substance acting as a weak base. Okay, we're still going to need an ice table. And so we're still starting off with 0.234 here. We're going to start off with 0 and 0 there. We get minus x there, plus x, and plus x. This is all the same as before. So 0.234 minus x, that's going to be equilibrium. And at equilibrium, I get x and x. And so now I can write that Kb equals x squared over 0.234 minus x. The problem is what about Kb? I'm only given Kas. And so you need another expression, and this is something you probably have to memorize. You have to memorize that Ka times Kb equals Kw for any particular conjugate acid conjugate base pair. And so that means that 6.3 times 10 to the negative 7th times Kb equals 1.0 times 10 to the negative 14th. And so I get, for Kb, I get 1.59 times 10 to the negative 8th. So now I can go ahead and solve. I can say 1.59 times 10 to the negative 8 equals x squared. And let's go ahead and assume that x is small and get rid of it. So over 0.234. At the end of the day, I get x equals 6.10 times 10 to the negative 5. And that does confirm x is a lot smaller than 0.234. So it was okay to neglect it. So what can I do with this? X is the concentration of HA and OH. Well, I'm ultimately trying to find out the pH, but unfortunately right now, all I can figure out is the pOH. So I can take the negative log of the concentration of OH, figure out the pOH, it's 4.2, and I have to remember that pH equals 14, that pH plus pOH equals 14, and I can then subtract 4.2 from 14 to get the pH, and I get 9.8. And so that is the final answer for the question.